Pure semiconductors, like a perfect silicon crystal, are really incredible materials. But here's the thing. In their pure state, their true electronic potential is kind of locked away. The key to unlocking it, believe it or not, is to intentionally mess with that perfection. So let's dive in and figure out how we can hack the crystal. So here's the game plan. We'll start with a quick refresher on how current flows in a pure semiconductor. Then we'll get into the brilliant trick that unlocks its true power. We'll look at how to create something called an N-type material, and finally, we'll explore the two different flavors of this whole process. All right, first things first. Before we can start changing how a semiconductor works, we've got to be totally clear on how it behaves naturally, in what we call its intrinsic state. So let's start with the most fundamental question. If you have a perfect piece of pure silicon, how in the world do you get electricity to flow through it at all?
Well, it all kicks off with energy. Even just the heat in a room can be enough to give an electron the kick it needs to break its bond and jump up to what's called the conduction band. But the really important part here is what it leaves behind, a little empty spot, which we call a hole. This team, the free electron and the hole, is our electron-hole pair.
Now, as soon as you apply a voltage, these pairs get moving. The free electrons, they're negatively charged, so they get pulled toward the positive side. That's our electron current. Meanwhile, other electrons hop into those empty holes, which makes it look like the positively charged holes are moving toward the negative side. And there you have it. That's our hole current. Okay, but here's the major problem. In a pure silicon crystal, there just aren't that many of these electron-hole pairs hanging around at room temperature. And that means its ability to conduct electricity, its conductivity, is actually really, really low. Way too low for the powerful electronics we use every single day. So we obviously need more charge carriers. But we can't just keep cranking up the heat. That's not a very controlled solution. We need a much smarter way to do it. And that brings us to the ingenious hack that is the foundation of all modern electronics, a process called doping. So what is doping? It's literally the process of deliberately adding impurities into that perfect crystal structure. I know, it sounds wrong, right? Making something impure on purpose? But by doing this, we can dramatically increase the number of charge carriers and just supercharge its conductivity. I think this analogy just nails it. You've got your team of identical silicon atoms. But by subbing in just a few different atoms, our impurities, you can completely change the electrical dynamics of the entire crystal. It's a total game changer. Okay, let's see this in action. We'll start by making a material that has a built-in surplus of electrons. This is what we call an N-type semiconductor. So to do this, we need a very specific kind of impurity, a pentavalent atom. Penta just means 5, so these are atoms that have 5 electrons in their outer shell. Things like arsenic or phosphorus are perfect for this job. So here's how it goes down. When you pop an arsenic atom into the silicon crystal, 4 of its 5 valence electrons form perfect bonds with the silicon atoms around it. But silicon only has room for 4 bonds. So what about that 5th electron? Well, it's just left hanging out. It's untethered, a free agent, ready to move around. And this right here, this is the magic of doping. We've just created a free electron, a mobile charge carrier, without having to generate a hole to go with it. We've added a player to the game without leaving an empty spot on the bench. It's a freebie. So when you do this with millions of these pentavalent atoms, the result is a material that is just swimming in extra free electrons. And because electrons have a negative charge, we call this an N-type semiconductor. N for negative. Simple as that. Okay, so that's one flavor of doping, creating a surplus of electrons. But what if we wanted to do the exact opposite? Now let's compare N-type with its counterpart, which we call P-type. I mean, this is the logical next question, right? We just saw what happens when you add an impurity with 1 too many electrons. So what happens if we add an impurity that has 1 too few? This slide lays out the beautiful symmetry perfectly. For N-type, we used a pentavalent impurity, 5 valence electrons, to donate a free electron. For P-type, we do the opposite. We use a trivalent impurity, an atom with only 3 valence electrons, like boron. When it tries to bond with 4 silicon neighbors, it comes up 1 electron short, and boom, it creates a built-in hole. In this case, these positive holes are the stars of the show. They become the majority charge carriers. So let's zoom out. The really crucial takeaway here is that doping gives us precise control. We can choose to create a material that's rich in negative electrons, our n-type, or one that's rich in positive holes, our p-type. This ability to create two complementary types of materials is the absolute bedrock of transistors, diodes, basically the entire digital world. And that leaves us with a really fascinating final thought. We've engineered two very different materials, one with way too many electrons and another with way too many holes. So the ultimate question is, what happens when we join them side by side? Well, that's where things get really interesting.